am Mr. Gallant.
And if you don't know who we are by now, you need to get woke.
That's true. And we're also Green Acres, and if you didn't know that, you need to get woke. And where we're at right now,
Unit COVID-19, how be Earth's place in the universe.
apparently we need to get woke too.
Right.
And what we're doing now is lesson 9. It's how did our solar system form. What we're going to be doing is kind of pulling all the information from the previous lessons, tying up all of our loose ends, connecting our dots. This is the last lesson of the unit. We're just going to kind of end it and close the book here.
So the icing on the cake.
Icing on the cake.
I like cake.
I like cake. So, first of all, we have to go back in time. We're going to kind of talk about how the solar system formed. And we have to go back about 4.5 billion years ago. And a nearby star, and by nearby I mean a couple light years away, very, very far away. A nearby star collapsed and it went supernova, gigantic explosion. Boom!
This sent large amounts of energy in many directions.
Okay? And eventually, that large amount of energy would hit just a random hydrogen cloud floating in space. And the energy, now hydrogen is one proton. But when it was hit by all that energy, those hydrogen, single protons each, would combine and create a helium atom with 2 protons.
Activation energy.
Activation energy.
Yeah.
And so eventually that cloud would start becoming all helium. But there's a problem, Coach Parrish.
This helium was unstable and eventually broke back down to hydrogen, so like an isotope.
Exactly. So there's no neutrons, so the helium would break down, it would go through decay, and it would break down and back into hydrogen. Now, it would actually release some energy, some more activation energy, when the helium would break back down into hydrogen, and that energy would cause other hydrogen atoms to combine again, basically creating a chain reaction. So you have these hydrogens become helium, they break apart, they make more hydrogens become helium, and it's releasing a large amount of energy and releasing a large amount of pressure.
Sounds like middle school.
Ah.
This pressure eventually caused all the hydrogen and helium reactions to compress into a ball.
So it's a giant hot ball of hydrogen and helium, which sounds like our sun. And this is how our sun actually formed, was due to a large supernova star, billions of light years away, going supernova, causing a hydrogen cloud that turned into helium, break back down into hydrogen, helium, hydrogen, compression, boom, our sun.
So you're saying our sun's story is a long, long time ago in a galaxy far, far away is what had to happen. Interesting.
We should make a movie based on that.
Yeah, that'd be a good title for some movie. Maybe like a movie series.
Ooh.
We could make 9 of them, if not 10.
Maybe 11? Maybe a Disney Plus TV series?
Possibly so.
Okay. Before Disney sues us, let's move on. Now we have our sun, so now we got to get the rest of our solar system. So what happens is, as we talked about in a previous lesson, the bigger you are, the more gravity you have. So the sun, being so large, began to pull on matter around it and cause the rocks and gases to start orbiting around the sun. But there was a problem with that.
All the matter was orbiting in many different directions.
So we actually saw this in our video, the one with the marbles and the weights.
Yes, that was actually really cool.
And he was making them go multiple different directions. Well, when they were going multiple different directions, eventually they would start colliding into each other, all the marbles, until finally there was one direction left.
They synced up.
Yeah. Exactly. So the rocks in space were going different directions, would eventually collide with each other, and they would form larger rocks as more rocks would collide into each other.
Gases close to the sun would be absorbed by the sun. Gases further away from the sun were able to be balled up and form large gas balls.
You get to say fun things in science and get away with it. Okay, so we have our rocky planets, we have our gassy planets starting to form, but not all the rocks form into planets. Sometimes these giant rocks would collide, but instead of forming a larger planet, they would collide and create small little pieces. And those pieces would stay pieces for a very long time.
And just move around?
And just move around in their own orbit as pieces of rocks rather than one gigantic rock. Okay? So, due to the collisions, everything in our solar system eventually would begin going the same direction, like we saw with the marbles.
Right.
So what would happen to the rock planets?
The rocks would stop colliding with rocks going the wrong way and begin to become the planets we know them today, Mercury, Venus, Earth, and Mars.
Okay? And then the gaseous planets, the giant gas balls.
The big gas balls.
The gas balls further out would absorb the remaining gases and become so large they would pull and gain some gravity, giving us our gas giants, which also have many moons. Because they had so much gravity, they would pull the remaining rocks, get a lot of moons, get some rings, which were moons that were colliding into each other. And that's Jupiter, Saturn, Uranus, and Neptune. And then finally we have our rock planets, we have our gaseous planets, and now we have
the rocks that collided but broke apart rather than becoming a large rock would orbit as random rocks, asteroid belt, and the Kuiper belt. Asteroid belt actually does separate the terrestrial planets from the extraterrestrial planets.
And Kuiper belt is actually where you find Pluto. So that was the argument, is that Kuiper belt is just a whole bunch of small little rocks, and Pluto was one that had formed up big enough, so it's a dwarf planet rather than being an actual planet. But that you would find that in the Kuiper belt.
But it's a sphere planet too.
It is, and it has a giant heart on it. The asteroid belt is actually very far spaced out. Scientists say you can actually stand on one asteroid in the asteroid belt and with the most powerful telescope not be able to see another asteroid anywhere around you. So that's why it's very easy to send satellites from Earth to the gaseous planets, because there's so much space. It's not completely dense with rocks. It's well built. So now we're going to go back to Earth. So when we go back to Earth, we're going to talk about the thing that orbits Earth, and that's our moon. So at some point, Earth was still forming. It did not have a moon. Earth has not always had a moon. But while it was still forming and becoming a solid, a large rock would eventually collide into Earth. What would happen then?
Well, this would turn Earth into a large ball of liquid rock.
And it would create debris. Almost if you take two rocks and throw them into each other, small rocks would create the debris. And parts of the liquid rock would become debris, and they would start to orbit around Earth, actually giving Earth a ring, like Jupiter, Saturn. Earth had its own ring billions of years ago. But over time,
eventually that ring would combine to become our moon. This is why the moon is made up of the same elements as Earth.
So we were actually, Coach Parrish and I were talking about this earlier. So you have all these, when the astronauts from the Apollo missions got rocks from the moon, brought them back here, and they studied them, they found a lot of the exact same elements that make up the moon make up Earth, the most important elements. But because Earth has an atmosphere, a stronger gravitational pull, it's a lot bigger, we're able to have more elements here, while moon has kind of pretty much stayed the same over billions of years.
Right.
So we have a little picture of it. You're about to watch a video on this too. But we have the moon colliding into Earth, creating the impact. There's our ring billions of years ago. And then finally that debris comes together to create a moon. Just like that.
So we think the moon formed when the Earth was struck by a very large object as the Earth was forming. So this would have been a separately formed planet that was vying for dominance in the inner solar system along with the Earth and other growing planets. But it collided with the Earth and ultimately was absorbed by the Earth and gave birth to our moon. So in terms of the impactor, which we often call Theia, we think that based on its mass, that it would have been as big as the planet Mars. Before it collided with the Earth, it would have had an iron core and a silicate mantle, like the Earth, and it would have had about 10% of the mass of the Earth. We think initially the inner solar system had maybe 20 small planets, and it was through collisions between these planets that we eventually ended up with our final 4 terrestrial planets. Now, the last of these big collisions on the Earth was the one we think formed the moon. From the perspective of someone on the Earth at the time, what you would have seen is an enormous object approaching the Earth, many, many, many times larger than the full moon in the sky. It would have hit the Earth at an oblique angle, On a time scale of a few hours, an enormous shock wave from the impact would have propagated around the entire surface of the Earth. The vaporized rock from the initial impact point would have been ejected out, and it would have flowed around the entire Earth. And the Earth would find itself enveloped by a thick atmosphere, but not like an atmosphere we know today. This would have been an atmosphere of vaporized rock with a temperature of more than 5,000 degrees. The momentum, the force of this collision, is enough to start the Earth rotating very rapidly. And so only hours after this impact, the Earth has a rapid rotation rate. Now we think on a much longer time scale of about 100 years. That disk will cool, the vapor will condense, and out of that disk, through collisions within the disk, the moon would have grown and accumulated. So although we think we have a good idea about how the moon formed, the exact details of this event are still being debated, and this is in large part a testament to how those samples that were returned decades ago are still driving active science debate as ongoing analysis provides us with more clues from those samples on how the Earth-Moon system formed.
Okay, Coach Parrish, so we kind of talked about how the solar system formed.
Yep.
Now let's figure out where we're at throughout space. Now, we know we're in Mr. Gallant's classroom at Green Acres Middle School, but we're actually going to zoom out a little bit more, and which puts us in Bossier Parish. Now, a little bit bigger than Bossier Parish is what, Coach Parrish?
Louisiana.
Okay, and we get a little bit bigger than Louisiana. It brings us to the United States, or America. And if we zoom out from the United States, it brings us to
North America.
So, of course, we don't stop there. We zoom out a little bit more, and that gets us to Earth. So we got where we're at now. We're right there. But we're going to zoom out more. And if we zoom out more, we're going to get our solar system, which is what we've been talking about this whole time. So here's our rock planets, the asteroid belts right here.
Yep.
Here's our gaseous planets. There's Uranus.
Ah!
And then the Kuiper belts right out here past Neptune.
Yeah, and Pluto's out here somewhere too. But I mean, look at the size difference.
You can't even see Mercury in this photo because they're trying to draw it to scale. They can't even fit the whole sun in here. So if we zoom out from the solar system, we get the
Milky Way galaxy.
Milky Way galaxy. And in fact, this dot right here is where our solar system is inside this galaxy. So you have to take the galaxy, you have to zoom in on that dot right there, you would see our sun, and then you'd zoom in and boom, you would see Earth. So the Milky Way galaxy is spinning, almost like water going down a toilet bowl. So these arms are slowly being sucked into the center there, where there's a gigantic black hole. And so eventually, over billions and trillions of years from now, our little dot will be sucked into that black hole, but you'll be dead by then.
Lucky you. Now, we know you can't see the black hole because it's not black. It's because all this matter is being pulled in and colliding as it goes in. That's creating all this radiant energy. That's why it looks like light.
And this is not an actual photograph. This is actually a computer image or an artist rendition. We actually can see a lot of the Milky Way in the nighttime sky. Not here because there's so much light pollution, but they're able to use what we can see in the night sky, and they're able to study other galaxies and actually figured out what our galaxy looks like. So if we zoom out from the Milky Way galaxy, there's actually other galaxies around us. And if you take all of the galaxies around us, you put them all together in one group, that's what's known as the Virgo cluster. So this is a very interesting picture of the Virgo cluster. It's a real photo. What? This is actually a picture from the Hubble Space Telescope.
That's a telescope that's in space.
And the reason it's in space is because a telescope on Earth has to look through the atmosphere to be able to see something. A telescope in space doesn't have to look through the atmosphere, so it gets a lot better images. So they pointed the Hubble telescope at a dark spot in the night sky, and this is the image they got. Every single light that you see is another galaxy. So there's multiple galaxies, and Coach Parrish, we're talking about some of the colors we see here.
Well, we see that we have, you can see we have these bright orange ones, these yellowish gold orange, which is like ours. And then we have these really bright white, bluish ones here, which these would be younger galaxies or stars in the galaxies, which are probably a couple billion years old. These here would be a couple hundreds of billions of years old. I mean, ours is
well over 4.5 billion, so we're probably
Right.
in the 50, 60 billion year old area.
right. And if it's hard for you to see on yours, but we have these red ones right here. This is a bright red. The red ones are called supernovas. And these are red dwarfs, and they're supernovas, and that's what means they've gone beyond critical, and they will either explode or implode when they go boom.
Remember we talked about how our sun was formed from hydrogen and helium? This galaxy has basically used up all of its hydrogen and helium. There's nothing
Right.
more to do the chemical reaction, so you're going to have one final explosion of energy as it runs out of its hydrogen and helium.
Correct, and it can make either a black hole, if it implodes, if it explodes, it can make a new star or nothing. Unless like ours, it chain reaction and then made ours.
Exactly. So the Virgo cluster is all of the galaxies that are right next to us, but there's galaxies further out. So if you take all the clusters and you map them in a computer program, you get a supercluster. So this is all the clusters we can see, all the clusters we can study. We put them into a computer program, and what we get is the
Laniakea?
Laniakea.
Thank you, videographer.
Thank
You are
you.
so welcome.
It's Hawaiian, and it means immeasurable heaven.
And so this is actually a computer-created image of every galaxy that we can see using land telescopes, space telescopes, different types of infrared images. We're able to map out all of these galaxies. And this little red dot right here, that is where the Virgo supercluster is. If you zoom in on that red dot, you have a whole bunch of galaxies, which is the Virgo, so there's the Virgo cluster, not the supercluster.
Which is the last image we saw.
Which is the last image we
all
saw.
those other galaxies.
And then if you zoom in even further, you would find the Milky Way galaxy. And if you zoom in even further, you would find our solar system. You zoom in even further, you would eventually find Earth. And if you zoom in further, you would eventually find the United States. And further and further and further until finally you get to you right here. So you have to think about the size of this thing. You're not even a speck of dust on this thing. You're smaller than dust. It's kind of crazy.
Yeah, like smaller than subatomic particles. That's weird.
And the supercluster was created probably back in the Big Bang. And what we notice is there's other larger branches off as the supercluster has been growing. And some scientists actually believe that these were smaller Big Bangs that actually created more expansion of space. And there's other superclusters around us, theoretically. And in between them is empty space or dark matter,
So like a chain reaction?
like chain reactions.
Interesting.
Very interesting.
Is it all coming from this point here?
This is kind of our starting point as it's moving away from this point. It's actually clawed, so you actually have it moving out from this point. Pretty cool.
Force pushing everything away.
Yeah,
Okay.
like
Cool.
an exploding grenade. What? So if we go from here, this is kind of as big as we know it as right now. This is as far as science has taken us. But we're going to zoom backwards a little bit. And we're actually going to go back to the Milky Way galaxy. Okay? So we talked about the Milky Way galaxy. It's actually spinning in a clockwise formation. Now, if this is our solar system, and this is the sun, and the whole galaxy is spinning, what does that mean our sun's doing?
Well, if that's spinning that way and we're there, I mean, it looks like a current, so it looks like are we moving?
Yeah. So like Coach Parrish said, it's like a current. we're following along with this as it moves and spins. And eventually, like I said, in trillions of years, we'll eventually be sucked into the black hole. So the sun, we usually get that image in our head that the sun's right here in the middle and all the planets are circling around it.
Oh, nice and flat.
Oh, nice and flat.
Like a tabletop?
Yeah, but we know that the sun is not staying still. The sun is actually moving. So it's not stationary, it's moving. And the sun has its gravity and its force, and it's kind of pulling these planets with it as it moves. So instead of being a nice flat table, it's more like a
corkscrew?
Like a spinning corkscrew. Okay, so back to our initial question, how did the solar system form? You think we answered that?
I think we did.
Yeah, I think we finally tied up all of our loose ends, put the icing on the cake.
Yeah, cake.
So that kind of finishes the unit.
Unit COVID-19's over?
Unit COVID-19's over.
The unit.
The unit. Ends our year, kind of, too. Yeah.
Sad face.
We miss y'all.
We do.
Even you.
Yeah, and you.
Yeah, I knew. So that's really it, Coach Parrish. We're kind of done. So we'll see you when we see you. And that's all, folks.
Good luck next year.
That's all, folks.